Alright, so this is just some formulas and some values. I don't think it's really needed at this point. It's just some of the handout that I found with other notes. Unfortunately, almost all the papers were from Miss England, and they were printed out, and I had to scan them. So a lot of them are faded after being scanned so many times. Um, so just some constants, though. In this class, I personally use more precise values than were given on this. For example, I use 273.15. I use 101.325. For calorie is 4.184. Some common. This is what would be provided on a STAR test if we had chemistry as being STAR tested. It is? I don't think so. Mm-mm. It used to be STAR tested, but I don't think chemistry is STAR tested anymore. Yeah, I'm not super certain. I haven't been doing any STAR. I don't STAR test any the materials. Mm-mm. I like that, but no, I do not like STAR testing. I've never done it, so yeah. Mm-mm. I'm not an administrator of it. I don't have any classes that are STAR tested. We had something other than STAR. Yeah, TOS. But this is what we've been providing if this was still STAR tested. So we have some common elements, a periodic table. Let's see what values do they use. Yeah, they don't even use the precise values that I use. Again, I'm way more precise than them. We have combined gas law, actually the more expanded version of it. We have Boyle's, Charles, um, and some other ones. Gala sauce. But this is the important one for now. Now this is duplicated. Typo is gay, not guy. So Boyle's law is PV, and it gives both versions. Again, I prefer the versions of the equations where all the initial values are on the left, all the final values are on the right. You can read over this yourself because I'm going to finish the PowerPoint today. Basically, I'm just showing you how to. It's just 3 example problems. Basically show you how to actually use these problems. So a gas, and I'm just rewriting the problem, occupies 473 cubic centimeters at 36 degrees Celsius. Find its volume at 94 degrees Celsius. And I've written it down on a piece of paper and just switching over to a piece of paper. So a gas occupies 473 cubic. I was just realizing that I wasn't recording the PowerPoint. It doesn't matter. I wrote it down anyway. Find its volume at 94 degrees Celsius. So in both physics and chemistry, this class uses algebra. I'm not an algebra teacher, but we use algebra, so I expect that you know how to do some algebra. But in physics and chemistry, the first step into solving these problems it usually begins with identifying your variables. Cubic centimeters is a value of what? A measure of what? Mass? No, mass is measured in grams. Length cubed is volume. So this is your initial volume. At 36 degrees Celsius, that would be your initial temperature. And it's asking you to find volume after it does something, so that would be final volume. And this would be final temperature. So the combined gas law is PV over T. And just memorize this combined gas law and you'll figure out all the other gas laws. So we know it's PV divided by T. We can put ones all on it and set it equal to PV over T and then put 2's all on it. So initial gas law is equal to final gas law. And then it's always good to rewrite your variables on the side you're given. So our initial volume is 473 cubic centimeters. And what would our initial temperature be? Would you write 36 degrees Celsius? You would put it in Kelvin. We add 273.15. So we add 273.15, and that gives us 309.15 Kelvin. And we are looking for final volume. Initial temperature was given as 94 degrees Celsius, but because this is an absolute temperature, it's a specific temperature, we have to convert it by adding 273.15, making it 367.15 Kelvin. Note, if you just memorize the combined gas law, you can get the others. So if the problem does not deal with pressure, assume pressure doesn't change. It's constant. By the way, a little algebra review. If I have the same number on both sides, does the number really matter? So if I were to divide both sides by 5, 5 divided by 5 is 1, so that's 1x. And 5 divided by 5 is 1 times y. 1 times anything, anything. So you can remove, if something appears on both sides of the equation, you can remove it. So if we assume that pressure doesn't change, that means that P1 is really equal to P2. And it's on both sides of the equation, so we can just remove it. Which gives us Charles's law. Charles's law is initial volume over initial temperature equal to final volume over final temperature. Now we can do some algebra. We're solving for final volume, so we can multiply both sides by T2. T2 divided by T2 cancel each other out. And so we have T2 times V1 over T1 equal to V2. Note, do you remember order of operations? So multiplication and division are on the same level, which means I can write this as T2 times V1 over T1. I can pull that up in the numerator because it's T2 times V1 divided by T1, so the multiplication comes first, so I can just combine the multiplication up top. And then once you have your equation set up, you can start plugging in variables. So T2 is 367.15 Kelvin. V1 is 473 cubic centimeters. And I divide that by T1. I highly recommend you put units on this. So we cancel out the Kelvin. They appear on both the numerator and the denominator, giving us just units of cubic centimeters. So if you plug that into the calculator, you get 561.74. Our only unit left is cubic centimeters. Yeah. Doing what now? So say that again. How'd you do it? So you take 400. So all you did, you can go back. So what you did is you ended up is you started out with V1 over T1 is equal to V2 over T2. What you did is multiply T2. You moved it from the right side to the left side by multiplying T2 here. Again, order of operations, it doesn't matter where the division and the multiplications are, they're the same level. So you did this in the calculator and then you multiplied it by T2. That's fundamentally the same thing as multiplying T2 by that. It doesn't matter what order, because multiplication and division are on the same thing. I could have, this is more advanced, I could have done 1 divided by T1 times T2 times V1. This is the same thing. In algebra, this is the same thing. You have a division. This is T1 is being divided, and you can always divide by 1, and it works out the same way. I don't care how you do your algebra, but I recommend you come up with the equation in algebra before plugging in any numbers, because if you come up with this equation, you can use this on every other problem that's like this. Again, these equations right now are simple, but in the future we're going to get some more complicated ones. So they use the alternative formula where it's all multiplication. So your given is 473 cubic centimeters. Again, you have to convert temperature into Kelvin. You're solving for V2, and you're given a temperature that needs to be converted into Kelvin. You know that this is going to use Charles' law because pressure isn't mentioned. It is very good that once you figure out which law it is, you always check your answer, and one way of checking your answer is to ask yourself, how is temperature and volume related? As temperature increases, what happens to volume? Well, as temperature increases, volume goes up. So you can look at your answer and see if your volume increased. If it increased, it probably means you did it right. So they start with this equation. Again, I would say don't start with this. Use the one I have. You can do this, but it might be confusing later. It doesn't matter which one you prefer, but I just suggest using the other one. So pressure is constant, so we can remove it from both sides. Plug it in. Here we can see need to solve for V2. We do that by dividing by 309.15, and we get the answer. By the way, significant figures. I'm still going to be using significant figures on the test, but it's not going to be something you really have to worry about. So this rounded to significant figures would be 560. So even though the calculator says it's 561.74, what you might see on the test whenever I give multiple guess is you might see 250, 430, 560, 780 as possible choices. You know, you don't really need to concern yourself with significant digits. You just choose the answer closest to wherever you got. Just know that the reason why it's slightly off on the test is because I rounded to significant figures. And this should have been 560 because the temperatures are only two significant figures. This brings us to this question. Note that it has a period after the 100, so this technically would have three significant figures. Again, I said that's improper to do that, or not recommended. You would write it in scientific notation instead. But a lot of papers and tests, it's really difficult to constantly write every number in scientific notation, as you have to add superscripts and stuff for the square. So they use this more informal method of writing significant figures. So all these three numbers have three significant figures. Let's go these. So a gas occupies 100 milliliters at 150 kilopascal. Find its volume at 200 kilopascal. So again, a milliliter is a unit of volume. This is the initial volume. Kilopascal is a unit of pressure. So that'd be the initial pressure. We're trying to solve for final volume at a final pressure of 200 kilopascals. So V1 equals 100 milliliters. P1 equals 150 kilopascals. We're trying to solve for final volume. And that's equal to 200 kilopascals. So begin with our PV divided by T equal to PV divided by T. It'd be initials on the left side, finals on the right side. We're not given temperature, so we can assume temperature is constant. So we can remove that. This makes us have Boyle's law. So this is Boyle's law. P1 V1 is equal to P2 V2. And we're solving for V2. To solve for V2, we would divide both sides by P2. P2 divided by P2 cancels each other out on the right. And so we're given that V2 is equal to P1 times V1 divided by P2. Now we can just plug numbers in. It's 150 kilopascals for P1, 100 milliliters for P1, and final pressure of 200 kilopascals. Very important to keep units here. In a little bit, I'm going to intentionally make a mistake. So kilopascals and kilopascals cancel each other out, leaving us just milliliters. So plugging this into a calculator, you get 75.0 milliliters. And that would be the final volume. Again, to check to see if we're right, we know from Boyle's law that pressure and volume are inversely related, meaning that if pressure increases, volume must decrease. So pressure went from 150 to 200, and volume went from 100 to 75, so that checks out. Everyone good? Yeah, eventually. So here, them solving it, all your given variables. So it's Boyle's law. As pressure increases, volume has to decrease. They start with this alternative formula, but temperature cancels out and they get the exact same thing. So you divide both sides by 200 and you get 75. So a gas occupies 7.84 cubic centimeters at 71.8 kilopascals and 25 degrees Celsius. Find its volume at STP. So, here, cubic centimeters is the volume, kilopascals is the pressure, and degrees Celsius is the temperature. So we have initial temperature is equal to, our initial volume is equal to 7.84 cubic centimeters. Initial pressure is 71.8 kilopascals. And initial temperature is 25 degrees Celsius, but we need to convert that into Kelvin. We can't use relative temperature degrees Celsius. We have to use absolute. Yes. Alright, so we're solving for final volume, and it's at STP. So standard pressure, and that would be 2, because we're looking for final. We have to look at what units here, because standard pressure is 1 atmosphere, but we're using kilopascals, so we use 101.325 kilopascals. Final temperature is 273.15 Kelvin, or 0 degrees Celsius. So PV divided by T1, PV divided by T2, and we plug in all these 1s and 2s. Note everything's changing, so we have to use the full combined gas law. And we are solving for V2 again. So here's an algebra trick for you. P1, V1, T1, and so again, you can change up the order of operations for multiplication and division because they're the same level in PMOS. So that means we can take this and write it as P2 divided by T2 times V2. It didn't really matter if I pulled this out though. But the trick is if you have some fraction multiplied to the variable you're solving for, you can multiply both sides. And I'm about to make an intentional mistake. You can multiply both sides by the reciprocal. The reciprocal of this is T2 divided by P2. So the reciprocal of this, so we can see P2 and P2 cancel each other out, and T2 and T2 cancel each other out. Did you catch the mistake? T2 divided by T2 does cancel out. So this means, again, this is a mistake. V2 is equal to P2, P1, V1 over T2, T1. I made this mistake during the 4th period, and it's here when I'm writing the units out that I realize my mistake. As soon as I wrote kPa and looked at my next pressure, I immediately knew I have a mistake. Because if I look at this, pressure 1 is going to have a units of kPa. Volume 1 is going to have a units of cubic centimeters. And this is going to be divided by a Kelvin times a Kelvin. So what are my total units? My total units are going to end up to be kilopascal squared times cubic centimeters divided by Kelvin squared. This is not the units for volume. It is very important that you keep adding these units to catch your mistake early. My mistake is I said you need to multiply the reciprocal to both sides. T2 divided by P2. This was where my mistake was. So let's start over. So I have my equation V1, or PVT, all ones, is equal to PVT, all twos. So it's being multiplied by P2 and divided by T2. In order to get V by itself, we're going to multiply by the opposites and divide by the opposites, meaning that if it's being multiplied by P2, we're going to have divide both sides by P2. And if it's being divided by T2, we're going to multiply both sides by T2. So we multiply by T2 over P2. So if we have a T2 on the numerator and a T2 on the denominator, they cancel each other out. And if we have a P2 on the numerator here and a P2 on the denominator here, that cancels each other out here. And so when I plug this in, V2 is equal to T2 P1 V1 over P2 T1. I can now take the values. T2 was 273.15 Kelvin. P1 was 71.8 kilopascals. And V1 was 7.84 cm3 divided by P2. P2 is 101.325 kilopascals. As long as you're not getting confused between P1 and P2 when writing these numbers down, the units are going to help confirm that our answer is correct. T1 is 298, or if you make the mistake of using Celsius, that's why you read and put the units. Because I can check to see that this, as long as I put in the correct value for P2, correct value for T1 in the appropriate space, I can check to see if this is correct by doing dimensional analysis. Again, the word dimensional refers to the units. It's really, dimensional analysis is just unit analysis, analyzing units. So I have a Kelvin on top. It cancels out this Kelvin on bottom. I have a kilopascal on top, which cancels out the kilopascal. My units are cubic centimeters, and that is a unit of volume, so I know this has to be correct. Plugging that in the calculator. Note, when you plug it into the calculator, you have to make sure the entire denominator is in parentheses. So when you plug that in, you should get 5.089678 cubic centimeters. So you can see here, I know my calculator's dirty. If you put in the parentheses on the denominator and press enter, my calculator nicely formats it to tell I'm correct. You get the correct answer. If I leave off the parentheses, calculator is going to follow order of operations. It's going to take, multiply, then divide. And because I didn't put parentheses on the denominator, this times 298 is not in the denominator. And so I get the wrong answer. During the dimensional analysis, I said you just multiply everything on top using multiply. And if it's on the bottom, we can just use division. So if it's on the numerator, I recommend using parentheses. Yeah, so if I put everything that appears on the denominator using a division symbol like this, note that it's different, but I still get the correct answer. So looking at what they did, they're given, so they extract their given variables. They know that they need to use the full combined gas law. And from the combined gas law, we know that as pressure increases and temperature decreases, volume is going to decrease. Because we know that as pressure increases, volume decreases. And we know as temperature decreases, volume also decreases. So it's being hit by two things. Again, they use this version of it. And here you can clearly see that to get V2 by itself, you need to divide both sides by 101 and 98. And they get the same thing. So I wanted to quickly go over the gas laws. So we have Boyle's law. Boyle's law says that, and let me turn this off real quick. That's a good time for a code word. Here's the code word. There's the code word. So we see that pressure times volume is equal to some constant. This means that pressure and volume are inversely has an inverse relationship, are inversely related. What this means is as pressure goes up, volume will go down. Or equivalently, pressure goes down, volume must go up. Or you could even write it backwards, as volume goes down, pressure goes up. Or as volume goes up, pressure goes down. Any combination of the four, or the two. So, name some examples of this. What's some examples of Boyle's law being applied? I'll get. There's another point I want to make. That's a good point right there. I'll add that to it. So, what's an example of Boyle's law being applied? What's something where if you change the volume, pressure changes? So, a bottle? What happens if I squeeze on the bottle and decrease the volume of the gas inside? The pressure is going to go up. So, pressure is equal to force divided by area. The area of this bottle cap stays the same. So, that means the only thing that's changing is the force. If the pressure increases, the force of the air molecules increase. So, if I squeeze this really, really tightly and increase the pressure, I would increase the force on this bottle cap, and I can even make it pop off if I press hard enough. So as I decrease the volume of the container, pressure is going to go up. One person suggested something that didn't make sense. They said, what happens if you have a flat tire? So when you get a flat tire, the pressure goes down. What happens to the volume? It goes down. Is that possible according to Boyle's law? So how does a flat tire cause the pressure to go down and the volume to go down? So these laws, these first laws that we're starting with, assume constant mass. Remind me, because last time I completely forgot. She's in my class. So the reason why why does a tire get flat? What's it doing? It's leaking mass or air. So if it's leaking mass, if the mass of the air molecules don't stay constant, this law doesn't apply. So if you're losing mass, this law does not apply. This law also depends, so all three of these laws depend on constant mass. This one also depends on constant temperature. Which means if the temperature or mass is changing, Boyle's law no longer applies. So we have to keep both temperature and mass the same. So for example, when I squeeze on this bottle, I'm not heating it up. So the temperature stays the same. Because the gas can't escape through the lid, because when I decrease the volume, that means the pressure inside has to go up. That's a guarantee. Because the mass can't escape, and the temperature is not changing. So let's do Charles's law. It relates volume and temperature. So, and this is a direct relationship, directly related. The direct relationship. What this means is as volume increases, temperature has to increase, or as volume decreases, temperature has to increase. Or we can put temperature first. As temperature increases, volume increases. Or as temperature decreases, volume decreases. So what's an example of this? Again, this assumes constant pressure. Yes. So what's an example of this? So what would happen if have you ever left a water bottle in your car overnight and you walked in and you saw it smaller? It shrunk up. It happens a lot over winter. You'll come in and see that your bottle has shrunken. It's been more crumbled. So you come over here and you see it pressed in slightly. What happened is the temperature overnight went down. And because the pressure inside the bottle has to match the pressure outside the bottle, because nothing is forcing it to stay small. Here, my outside force was forcing it to stay small, but because if you have because the only thing forcing it is atmosphere, and so atmosphere is pushing it to a smaller size, and it'll stop whenever the pressure inside matches it. If there's an unbalanced pressure, then it has to equalize. So it will shrink because the atmosphere is pushing it closed. And so as the temperature falls down, the volume of the container has to shrink to match up with it. Another example would be a hot air balloon. As you increase the temperature of the gas inside the balloon, the volume of the balloon has to increase. If you take a balloon and put it in the freezer, you would notice the balloon shrink. And lastly, we have Gay-Lussac's. And this relates pressure and temperature. Again, this assumes constant volume. And again, we could say that as this is direct, as pressure increases, temperature increases, or as pressure decreases, temperature decreases. Or you can reverse them, temperature increases, pressure increases, or as temperature decreases, pressure decreases. So what's some examples of Gay-Lussac's law? So imagine you had a steel can, like a Coke can that can't easily compress. So and then you heated it up. If you heat it up and the gas inside it gets hot, the gas can't cause the metal container to move. So you're going to have a buildup in pressure. So as you increase the temperature inside, the pressure is going to go up. So when you're driving your car and they're fully inflated, as you drive, friction causes the air inside your tires to heat up. And so the pressure of your tires, if you have an electrical gauge on them, you actually see the pressure increases as you drive. If it's no longer able to expand and get larger, assuming that volume stays constant. Another example, it would be if you climbed up to a higher. If you were to cool, like go up into a mountain, and there's other reasons for this too. But as temperature decreases, or the pressure inside, like if you had a room and you cooled it off, the pressure inside the room would drop. Here's another example. Let's look at a piston. So when a piston pushes down, so how a car works is a piston pushes down on gas. So it takes gasoline or diesel and makes it into vapor, and it compresses this gas, and it's to where the temperature increases very high, and it causes it to ignite or burn in 2 minutes. Does this fit any of the laws? So let's see. As volume decreases, temperature goes up. But I said over here, as volume decreases, temperature is supposed to go down. So why doesn't this work? Why doesn't that work? So when does this law only work? It only works when pressure stays constant. If I squeeze on the gas, if I press really hard on the gas, pressure is going up. So pressure is no longer constant, so this law fails. Yes. So if we look at this, so I'm increasing the pressure, and temperature is going up. Well, this works out, even though the volume isn't staying constant. But again, you really can't use this law. My point was you can't use these laws if the constants aren't there. Sometimes they work, like in this example, I'm increasing the pressure, which is causing the temperature to increase. So volume is going down, and then that means that pressure must go up. So that works. So what you see happening, you're kind of correct, is these two conditions are better than this one condition. You have two things happening, and these outbeat this one. That's it for today.